we're going to have Lauren talking to us about how you can understand native iOS from an Android perspective. This is increasingly important, especially as so many of us are starting to delve into Kotlin multi-platform, and you need to sometimes have an understanding of iOS. So I'm very excited for this talk. Lauren, before we get started, do you have any words you want to say?
Thank you, Victoria. I just hope everyone enjoys this talk. I just also wanted to say that in the Slack channel for this talk, I have already posted the slides as well as the GitHub repo if you're interested. I hope you enjoy it. Thanks.
Awesome. Thank you so much. Yep. Feel free to join that channel, ask questions as we go, and let's get started.
Good afternoon. Thank you for giving me the opportunity to speak with you today, and welcome to Understanding iOS from an Android Perspective. I'm Lauren Yew, and I'm a staff Android engineer at the New York Times, where I develop and integrate our Android and iOS core feature libraries into our mobile apps. Today we're going to take a look at developing for iOS from an Android perspective. So before we get started, let's start with a caveat. For simplicity's sake, I'm going to be focusing on Swift and Kotlin as well as the latest iterations of iOS development and Xcode. Now, for this presentation, we're going to be comparing the iOS and Android apps and platforms. For these comparisons, iOS will always be on the left and Android will be on the right. And for some of these code and app example comparisons, I'm going to be using my Pet Adopt sample app, which was built off of PetFinder's free database backend to search through thousands of animal welfare organizations to find adoptable animals for a given query. Now, this Pet Adopt sample app that I built has both Android and iOS versions, with each feature mirrored per platform. These are the topics we're going to discuss today. First topic is the design differences between the Android and iOS platforms. So iOS apps and platforms are designed based off of the Apple Human Interface guidelines, whereas in Android we use material design. So one of the main areas that the platforms differ is with the phone's controls. So in iOS, we only have a home button, which is triggered for newer phones by swiping up from the bottom of the phone, and on older phones you'll actually see a dedicated hardware button. Whereas on Android, especially when we're dealing with apps, we always have a home button and a back button available. Therefore, when you're working in iOS apps, the only way to truly exit the app is through the home button. There is no back button that's always available. If you see a back button, it's actually being shown by the app itself and is used for navigating within the app. Therefore, iOS does not have a on-back pressed back button specific callback for exiting the app like we have in Android. Instead, they have view will disappear or on disappear, which is called whether we are navigating forward, backward, or exiting the app in iOS. Speaking of controls, iOS does not have radio buttons like Android does to select a single option from a group of options. Instead, an iOS developer can use a segmented control if they only have a few options to choose from, or create a picker if they have multiple options and want to create something like a spinner to choose an option from this group of options. Or an iOS developer can create their own list in which they program that list to show a checkbox on a single option chosen out of that group of options. Likewise, an iOS developer does not have the checkboxes that Android does to select multiple options from a group of options. Instead, an iOS developer can extend that list they created before to have multiple items checked, or the preferred way according to the Apple Human Interface guidelines is to create a switch per option to toggle on and off each option. And finally, one of the major areas that iOS and Android design differs is in how errors are handled. According to the Apple Human Interface guidelines, errors should be handled with the alert error dialogues. Now, some iOS developers also choose to use the red error label text to simulate inline errors, but in general, the alert error dialogues is how iOS shows any kind of error. This is very different from Android, in which, according to material design, we should not be using these error dialogues unless we have major blocking errors, and instead we generally use inline error text or some kind of snack bar error. Okay, let's move on to the next topic, Swift versus Kotlin. Let's start simple with declaring variables. In Swift, we use let to declare a constant variable equivalent to val in Kotlin. And in both languages, we use var to declare mutable variables. Now let's move on to optionals. So in both languages, we can use a question mark on the type to mark a variable as optional or nullable. And note for Swift, we use nil for null. Now, say we wanted to use an optionals field or call a function on it, we can use the question mark dot syntax in both languages. This is known as optional chaining in Swift and a safe call in Kotlin. Basically, this allows us to only call that field or call that function if the person variable is not null. Now, say person is null or name is null, and we want to provide a default value. We can use double question mark syntax known as nil coalescing in Swift, which is equivalent to the Elvis operator in Kotlin to provide this default value. But the main area where Swift and Kotlin differ with optionals is that Swift does not imply that a variable is not null, even if we have a null check around it. The same applies for typecasting. So for example here, even though we've checked that human is a type of person, when we use human as a person, we must force unwrap it in Swift, unlike with Kotlin where this is implied. And equivalently, even if we force unwrap a person, for example, force unwrapping it to be not null, every time we use it, we must force unwrap it again. Unlike with Kotlin, in which once you do one force unwrap, it is future inferred to be not null, for example. So how do iOS developers handle optionals or typecasting? Well, we can use the guardlet or iflet syntax to specify a new variable or use the same variable name and make that new variable satisfy a given condition. Now, the main difference between guardlet and iflet is that guardlet will usually return or throw an error in its else case. This follows the pattern of early exit, where we have our assumptions at the top of a function, and we exit the function if those assumptions do not pass, and continue in the function should they pass. Thus, after the guardlet, the variable is set to its new state. Unlike with the iflet, where the variable is set to its new state only within the scope of the iflet. This is more helpful, for example, if human is a person, then we can do something within the iflet, otherwise we can do something else in the else case and then continue on in the function. Let's move on to functions themselves and look at the difference between Swift and Kotlin. Now in Swift, we declare functions with the func keyword equivalent to the fun keyword in Kotlin. Now let's take a look at returning in functions. So in Swift functions, we can have an unlimited number of values returned in our function. Now, it is suggested that if you have a large number of values returning, you return a struct or a class instead. However, in Kotlin, on the other hand, we can only return a maximum of 3 values in a function with a pair or a tuple. And should we want to return a larger number of values from a function, we must create a new class. Now let's take a look at specifying parameters in a function. You'll notice here that I have an underscore in front of my first name parameter in my Swift function, and this allows me to, when I call the Swift function, not to have to provide the parameter name and type it in. This is very different from Kotlin, in which we can choose to specify the parameter name, but in general the parameter names are automatically implied based off of the parameters order in the function. Now let's take a look at some things we've been using behind the scenes. Protocols, structs, and classes. Now, protocols are equivalent to Kotlin interfaces with one exception, and that being that protocols cannot provide default implementations. So in order to do so, a Swift developer can choose to create an extension of the protocol, more on this later, to provide this default implementation. Now let's take a look at structs versus classes. Both structs and classes can provide stored variables or functions. But the main difference between the two is that structs are value types, meaning that when you pass them around, you're actually passing a copy of their value. Now, Kotlin does not have an equivalent to structs, but this would sort of be like having a data class that you ran a dot copy on every time you pass it around. So what this means is that, for example, if we have a person struct and we pass it to a person2 struct and we reassign it, even though we've reassigned it, we're actually passing a copy of its value. So if we change the name field to Julienne, then you'll notice the original person struct doesn't change its field value because you're actually just passing a copy of it, not the reference. So this is opposite to the dog class, in which when we pass it around, we're passing a reference to it. So when we change the name field, we're actually changing the original dog. Another difference between structs and classes is that classes can inherit from other classes or be inherited from, unlike with structs where we cannot inherit or be inherited from. Now, both structs and classes can implement protocols, but only classes can do inheritance. Now let's take a focus on classes in Swift versus Kotlin. And there's a big difference between the two in how they handle inheritance. So in Swift, all classes are by default open. So meaning that within the same module, you can inherit from any class unless it's specifically marked as final. This is opposite from Kotlin, in which all classes are by default final, and then we must mark a class as open in order to inherit from it. Now, when we're talking different modules, so in Swift, when we're trying to inherit from a dog class, say it's our library module and we're an app module, then we must mark a class as open. And this does follow the same paradigm as Kotlin, so that a class must be open to inherit from it. Now, as promised, let's talk about Swift extensions. All protocols, classes, and structs are extendable. And this allows developers to add more functionality, change functionality, or add new protocols to each extension. However, adding new stored variables is not allowed. So as such, you can expect in a file that has a declared struct, protocol, or class that you can have extensions that extend new features with more functionality or more protocols to help modularize the code. Now, these extensions can actually happen within the same file or a different file, similar to the Kotlin extensions. So if you want to see where your classes have extended, it's best to search for it by name. Okay, let's move on to app setup and structure. First, let's start off with some Xcode basics that apply to app structure. So when you open up an iOS app, you're either going to be opening up your project or your workspace. If the workspace is available, you should always use this option to make sure your projects are properly loaded into Xcode. So what is a workspace? At a high level, it's a document that tells Xcode what projects or other documents that it represents. And a project represents an app, library, or framework, and it contains things like what are the source documents, what is the file structure, what are your basic project-wide settings. You can think of this sort of like Android's root build.gradle. And a project contains one or more targets, and a target tells Xcode how to build or run each app or library. You can think of this like Android's app build.gradle file. So when you open up your workspace in Xcode, you'll see your projects. If you click on a project, you'll be taken to your project-wide settings, which also includes all of your targets for that particular project. Should you click on a target, you'll be taken to your target configuration in Xcode, which has important things like your unique bundle identifier, which you can think of as equivalent to the Android application ID. It also contains things like what frameworks or libraries that particular target depends on. And if you go to your build phases, you can see the compile sources associated to this target, which is what you're setting when you set a target membership onto each file. Okay, let's move on to iOS app structure. First off, some terminology. When I refer to a bundle, I'm talking about the executable app or framework. A framework is basically the equivalent to an Android library module. And going back to, for an example, an iOS application and what's required to build it, we have our application bundle, which consists of an info plist, and this is a kind of like a configuration of how to build and run your app, and your executable, and your resource files. Let's take a closer look at the info plist. Should we open in Xcode, you'll often see it look like this kind of table, and its full name is information property list. It's basically similar to the Android manifest as well as parts of build.gradle. And essentially, it's actually an XML file encoded with UTF-8. So if we were to take a look at the source version of this table that we see in Xcode, it would look like this. Now, if you're thinking that parts of your info plist look awfully familiar, that's because you've seen it before in your project-wide settings or your target configuration within Xcode. So every time you change these settings, you're actually either updating your info plist or updating the pbxproj file, which is part of your project-wide settings. Now let's talk about working with dependencies. So a lot of iOS developers use CocoaPods, which is a third-party scripting library, to hook in dependencies into their Xcode app. Also, iOS developers can use SPM or Swift Package Manager, but for this presentation today, we're going to be focusing on CocoaPods. Now, as I mentioned, CocoaPods is a third-party scripting system, and basically what you do is you specify a pod file to specify your dependencies, for example, which you'll see here, and then you'll run a script, and then CocoaPods will use Ruby to automatically install those dependencies into your Xcode project, into your targets as the appropriate dependencies. Now, let's compare the pod file specified in CocoaPods versus a build.gradle in Android app. So in CocoaPods in the pod file, to specify dependencies, we have to specify what target we want these dependencies for. And this is because CocoaPods is essentially this third-party scripting system that's outside of our project. So it needs to know exactly what target we want our dependencies on. This is very different from the build.gradle in our Android apps, which we specify dependencies, and then the build.gradle automatically knows which app we want to specify our dependencies for based on its location and its file structure. So, going back to our pod file, we specify our dependency by the pod keyword, give it the dependency name and a dependency version. This is essentially equivalent to the implementation in our build.gradle, which we specify a package name and then give it a package version. Now you might be asking, how can we just specify a dependency name and then just automatically get this dependency? Don't we need to do something like a Google or a Maven to specify what repository we're getting this from? Well, actually, CocoaPods has an internal central repository, which it calls trunk, that provides its libraries or pod specs for all of its scripts to just look up by name. This makes it really easy for iOS developers to publish libraries or find libraries just by name. In CocoaPods, you can also specify a pod spec or your library with a URL, and this makes it really easy for iOS developers to develop internal iOS libraries, publish them on something like GitHub, and then easily find that with their CocoaPod scripts to provide those as dependencies. Now, once you've specified your pod file, you run your script, which for example would be a pod install. CocoaPods will then download all of your dependencies, source files, and header files into a pods project, which is our framework project, a library that will be available, and it will automatically hook into your Xcode's targets build phases to embed those as dependencies for your specified targets. Now, what are some example popular iOS third-party libraries? Well, we have Almofire or AF Networking, which does HTTP calls. It's very similar to Retrofit. If you want to do image rendering, there's Lottie, which also does animation rendering as well. If you're an Arch Java fan, there's an RX Swift, or if you can just use Combine, which is actually built in with the Apple development environment. And if you'd like a SQLite database very similar to Room, there's also Yap Database. And finally, if you want dependency injection very similar to Hilt, there is a third-party library called Resolver. Okay, let's move on to app lifecycles and architecture patterns. So if your app has not been run or it has been terminated, it's in a not running state. When your app comes into foreground and is starting to load but cannot yet receive our user events, we have an inactive state. Then when the app is ready to receive these user events, these user inputs, we have an active state. Let's say your app is going into background. It's going to transition back to inactive, then to a background state where it can execute some code. From there, it can come back into foreground and then transition back to inactive, then active state. Or if it no longer has some code to execute, the OS will automatically put the background state back into a suspended state. From there, say we have a pull timer wake up to do some executed code, the app can come back into background, go into background state, or if the OS decides running out of memory, it can terminate our app and then we're back to a not running state. So how do iOS developers handle these application lifecycles? Well, we can use the app delegate, which is a singleton application set of callbacks for our application lifecycle, or our scene delegate, which has callbacks for Windows. So think iPads of multiple windows to handle our UI lifecycles. Now, if you're working with a Switch UI app, you can configure your app to use app delegate for these application lifecycle callbacks, and they have a new class called Scene, which was going to replace our scene delegate. Let's take a look at some app lifecycle callbacks with the app delegate. Say we were not running and we finished our launching, we're coming into foreground, we have the application did finish launching callback. Then when we're coming into foreground, we're coming into this inactive state, we have the application will enter foreground callback. Then if we're coming into active state, we have become active, we have the did become active callback. Should we go into background, we're transitioning back into inactive state, away from active state, we have the will resign active callback. You get the gist. Now let's move on to some common architecture patterns. Common architecture patterns in iOS are very similar to Android. We have MVC, or Model View Controller. This is also unfortunately known as Massive View Controller because often our view controller becomes really big, hard to modularize, and is just this god class that's controlling all the model's views and business logic. Now this was the way that iOS was originally meant to be architected when we were back in Objective-C land. There was actually a UI View Controller class that was originally meant to talk to all the views and then work with the models. However, architectures have changed. We now have model view presenter, with presenter basically replacing our view controller and being a class that the developer creates. Unfortunately, like in Android, this can often suffer from the massive presenter problem. We also have an Android favorite, model view model. We're going to get more into this one in a moment. And for those ambitious modularizers, there is Viper. Unfortunately, this Viper is quite complex as an architecture, so for this presentation, we're going to be focusing on MVVM. Now, it's important to note for Android developer getting started developing for iOS that with view models in MVVM, there is no built-in view model class or type in iOS that controls lifecycle and all those niceties that Android has. Instead, if you see a view model in iOS, it's actually a regular class that an iOS developer has created that usually has some properties or functions for the view to react off of or update. And it's totally up to the developer on how much business logic they'd like to put in this view model class or to put in something else like a repository or a model, etc. Okay, let's move on to everyone's favorite topic, Swift UI versus Jetpack Compose. So when we build a Swift UI view, we specify a struct of type view. This is a Swift UI type that requires us to have a var body of some view that will have some content. This is equivalent to in Jetpack Compose when we specify a composable that has to have some content. Now, this particular Swift UI view is building my pet details view and has the equivalent in Jetpack Compose. And you'll notice in my Swift UI view that I have a name and an update favorite status lambda, which are parameters or state that I'm passing in. This is very similar to in Jetpack Compose where we have our parameter state or we declare some state, so that way we can get some content to fill in our view. Now, in Swift UI, we use a VStack for columns and an HStack for rows. So here we have an image view side by side in our VStack on top of our HStack, which is our row of text. This is how we're able to get this image of cat above this row of text describing the cat. Now, how about customizing our Swift UI views or modifying them? So in Swift UI, all the Swift UI views have builder functions that we can use to customize or change the feature functionality of these Swift UI views. This is equivalent to Jetpack Compose where we have these modifiers that we can use to do the same. So here's an image side by side in Swift UI and Jetpack Compose, and you'll notice again in Swift UI we can use these builder functions to adjust this image Swift UI view, similar to how in Jetpack Compose we'd have a modifier that would do something similar to our loading image view, which is a custom view in Jetpack Compose that I've created. So now that we have an idea on how to build a Swift UI view, how do we get the data to the Swift UI view? Well, we can either pass that data into our constructor, into, for example, home view, or we can use the environment object builder function to pass, for example, our state object for, in this case, our home view model to that Swift UI view and to any of its children, in which we can get an access to that environment object with the @environment object annotation to be able to access that view model we passed in. This is very similar to Jetpack Compose, in which we can pass our HILT view model into, as a parameter, our Jetpack Composable, and then we have to pass it down as we go. That's all for me today. Thank you all for coming, and I hope you learned something new about iOS development. If you have any further questions about Android or iOS, or want to see some more examples about Swift UI versus Jetpack Compose, you can check out my Pet Adopt sample app, which I will be providing a GitHub link to. Are there any questions?
That was such a great talk. Thank you so much, Lauren. I know there's been a lot of chatter in the Understanding Native iOS from an Android Perspective channel. If you have questions, feel free to drop them in there. I know I'm going to be coming back to this talk the next time I have to do anything touching iOS. We'll give it a couple minutes for questions, and we'll be jumping right into the next talk in a moment, so stay tuned for that. And remember, we do have the channel's still open from previous talks. If maybe you thought of something that you forgot to ask about, feel free to drop that in, and the speakers will get to it when they're available. All right, we have one question here. Do you have any thoughts on Swift structured concurrency versus Kotlin flow?
Yeah, I was just about to answer that in the Slack channel. So I would say that the async await is very much like Kotlin coroutines. And if you want to think of something that's more like flow, you're looking at something like combine. Does that answer your question?